Jimmy, can you hear me? Guys, please put on your safety goggles or you're not allowed beyond this point. And when you're inside, you should be inside the net. Thank you so much.
Test, test, test. Good afternoon or good morning, friends and family. Give the drone teams about 20 minutes and then we'll start the actual event, okay? Thank you guys. Now will be a good time to grab coffee, lunch, breakfast, whatever you're in the mood for in the meantime. Thank you. What's your social security?
Yo, any shout outs?
to BWSI Autonomous UAV Racing Course 2025. We have our first team up, Firefox, starting off their race. I'll be your host today, Chris Rincon, and as well, here with me, our commentator.
Anubhav Dikshit, I will be calling the races as they go on.
Perfect. As the team goes, I like to list off a couple rules for our team members. Number 1, teams can choose to have obstacles or no obstacles. The slowest obstacle time beats the fastest no obstacle time. Number 2, teams are based on total off-board time taken to complete the race. Time for manual takeoff and landing is excluded. Final rule is if teams switch to manual during the race to prevent any crashes, of course, their time is stopped. The drone is moved back 5 yards and time is restarted after takeoff. Thank you, ladies and gentlemen, and enjoy the race. We have 5 teams performing today, so best of luck to all.
Let me
Are they actively going? This is like.
I'm timing.
Okay, so we can start commentating this.
Yes, that's good.
Okay, great. So now, let's talk about what's happening. Firefox is doing a pretty good job staying along the line, stuff like that. Yeah.
So far, Firefox has done a pretty great job of following the line. Battled the curve very well. Wonderfully past the first obstacle. Coming up on the second obstacle now.
No, but take over.
Through some turbulence, it has made it past the second obstacle. Coming up on obstacle 3 and the finish line, the path is going great. Coming up, it's going. And a little too low. Overall, a wonderful performance so far on the test run. This is going well.
Let's give it a round of applause.
Let's give everybody a round of applause for this performance. Give it up for Firefox, everybody.
Sakina, they're gonna go again.
Current time is 2:34.
Current time is 2:34. And up again for the second attempt. Firefox is in the air. And it has started its path follow. It's coming up on the final obstacle now. Attempt 2. The height has already been adjusted and it's going great. And it has passed the final challenge. Give it up for Firefox, everybody. A time of 2:59.93. Firefox is starting their second run to attempt to see if they can do it in one way. And we're off. Drifting a tad bit, but it's still close to the line. They will be calling it.
Take off at the same height every time. That run may be disqualified. Alright, ref clocking in on the first lap. We have confirmed that the reason they passed the last obstacle may have been because they just changed the takeoff. In future rounds, we will mandate equal takeoff height at all times along the track. That run may be disqualified.
Please give the team 3 to 5 minutes to set up for a second round attempt. As we wait for the second round of attempts, let's talk about some fun facts about UAVs. The first UAV flight dates back to 1916, called the aerial target, essentially a flying bomb. Some UAVs are modeled after insects and birds for stealth and agility. Swarm drones can fly together like flocks of birds, communicating and coordinating in a real time. Companies like Domino's and Amazon have tested drones for pizza and package deliveries. Powered up for Flight 2, Firefox is elevating into the sky. They have locked in the starting height and they're ready to go. Autonomous. Fireflox fires a path down, following the edge. Steadily and surely, it follows the curves well. Coming up on this curve, it's going great. And they have rounded the curve perfectly. Coming up on obstacle 1, a little off track. Very off track. And back on course. And they have landed. Time is clocked at 43:57 right now.
Quick rule change. As we recall, rule number 3, if teams switch to manual during the race to prevent a crash, their time is stopped. The drone is moved back 5 yards. 5 yards have been switched to 10 feet, and time is restarted after takeoff. Thank you.
Follow the curve, 1 second off. Firefly is taken off. Too high. Firefly coming up on the second obstacle. At a perfect height to enter it. And Firefly has defeated the second obstacle, coming around on this path now. Unfortunately, we're slightly off track. He was back on the path. Following the straight line perfectly around this curve, missed the final curve. They're still gearing up towards the last obstacle of this course. It needs to go slightly higher. And it is perfectly gone through. Give it up for Firefox, everybody. Time coming in at 2 minutes, 26 seconds, 0.77 microseconds. Team Firefox has 6 more minutes to attempt this course one more time, and then they will be giving their presentations to you all. Team Firefox starts up again. For their final and third attempt, they made the adjustments. Now they're ready to go. Steady in flight, they have now gone autonomous. Coming up on this line, they are following it to the T. And around the first curve, they're battling it very well. A little higher in altitude now, and they continue to follow the line perfectly, faster and better than before. So far, this flight has gone perfectly, and they're coming up on the first obstacle. The drone seems to have recognized the AR tag, and it is now going a little high. Unfortunate setback, but great flight so far. They've decided to call this attempt and restart entirely. Smart move based on the penalty for going manual.
Drone fun fact, UAVs are now used in Hollywood to capture stunning aerial footage, way cheaper than helicopters. Some researchers are working on drones that could pollinate crops like robotic bees.
And here is the fourth attempt from Firefox, likely to be their last. Let's see what they have in store for us. And we're autonomous. Following the line perfectly so far, moving at a fast pace. They battled the first slight curve, coming into their first big curve. And that rotation looks so seamless and perfect, they're going great. A little low. The drone seems to just be following the path. at a more measured pace now, but still steady. The line following for Firefox has improved drastically, and they're doing great. Coming up on obstacle 1, the AR tag. AR tag in clear view. They have decided to restart again. Team Firefox has 2 minutes left on the clock. Time has elapsed right now, though. And Team Firefox is in the air. 2 minutes left on the clock. This is going to be their final attempt, most likely. Firefox is following the line seamlessly. Once again, never seems to be the problem. They have mastered the art of line following in these stunts. First curve, gone. A little jump. Lowering more. Interesting strategy. Could be so that the drone can see the line better through its camera. It is drifting. They have called it. Time is over. Give it up for Team Firefox, everybody.
Two minutes and 26 seconds is Firefox's best time. Now introducing the team for a quick presentation on some of the skills they learned these past 4 weeks.
Hi, we're Team Firefox, and we're going to talk a little bit how we do the challenge. I'm Claire.
I'm Sonia.
I'm Kaylin.
I'm Jimmy. I'm Pranav.
And I'm Pico.
So first about the costume.
not working. Use the other one.
Yes, the other one. There
So after our camera takes the picture, we use masking to eliminate the unwanted colors, and then that gives us a grayscale image. But that's image still has pixels in various shades of gray. So we then do thresholding, which is essentially where we brightness threshold, and then anything above that will be considered white, and that is the line, and anything below that is considered black, which is the background. And in that way, we can convert a raw camera image to a binary image, which we can then run line following code on.
However, sometimes, as you can see, there's a few pieces of tape that still get stuck in the final image. So then we use contouring to isolate different shapes, and then we filter them by arc length, so then if the contours are too square, we no longer count them. That allows us to get a final line that is pretty good, and then we can run linear regression on it to get the proper vector.
So should I tell them? Yeah. What, you want to go up and teach him?
No, the audio guy has got to come back and fix.
Yeah.
I can hear. We're hearing them on the webcast. Everything's fine.
But it's fine. Yeah. Okay.
Okay, so on the screen right now is our line following running in SM. And basically what it does is that it takes that linear regression and it returns 4 parameters, the x, y, which is the center of the line, as well as the vx, vy, representing the velocity vector that the line is currently pointing towards. So we define the top left of the image as 0, 0. So any negative y value going downwards, or, oh. Okay, it's fine. Okay, so any negative y value will be considered going forward, which is why here you would see a y that is vy of negative. So that will basically tell the drone that I want to move forward. I see a line that's pointing forward. I want to go that way. And in the x direction, we also compute the x offset, so the horizontal offset of the drone to the center of the line, so we don't stray off course to the left or to the right. And it does this by the target point is extrapolated 300 pixels from the center of the line.
So these are AR tags. These are fiducial IDs. To use them, we first have to calibrate our cameras. Oh, we have to calibrate our cameras. First, we use the focal lengths and the distortion coefficients to get matrices that we can feed into an open source library called OpenCV. And that detects the AR tags, and we can get our translation and orientation from it. And to see how we use those, Kayla.
So using our position from each AR tag, we're finding the relative position of each AR tag, which we map in a dictionary so we know where to go. For example, if we see the AR tag that it's at the bottom of the circle, we know that we want to be the radius above it. So then we use a PID controller to tune our velocity to go to that desired height. And that's how we make it across all the obstacles.
So we had a lot of struggles in the way. So our main struggle was us converting from ROS to Mavlink. So ROS is like the determined framework we're supposed to use in this course. But we were using an interface called Micro XRC DDS to communicate between our Raspberry Pi and our flight controller. But the reason why we converted is because we can't get reliable yaw data. So in the simulation you were seeing, we could get perfect yaw data from the simulation because the physics in it are like perfectly just accurate, ideal. But like in the real world, there is like lag between it, and like sometimes we just can't get the yaw data at all, and that's why we can't convert into the coordinates that are needed to navigate our drone in using the Micro XRC DDoS protocol. So we had to switch over to Mavlink. To then be able to send our coordinates in a body up or body down frame, which is a different way to our drone, so it can follow the line. So we had a lot of troubles tuning it. So you could see here when we tried to follow the line, the drone's just shooting up by itself, and we were not able to save it, and we had to replace the arm afterwards. So you can see we had to go through many iterations of our code, and it was just a struggle, basically. Okay, today, actually we have an answer of this, because today we're eating malatang over in downtown Boston. Yeah.
Great job, guys. Congratulations. Now up, the second team of the day, Lynx.
Lynx is going to be starting testing soon. It is not their final run. Lynx is up in the air for their first test run. Settling at a height perfect for obstacle 2. And it proceeds onwards. A tad bit too high for obstacle 2, but now they're adjusting their height correctly. Just to remind the audience, this is a test run. They are just testing their drone out for now.
So we have one member from the team Firefox. If you want to quickly introduce yourself to everybody.
Okay, hello everybody. My name is Jimmy Joe, and I'm from Kentucky.
Awesome. So one quick question about your team and yourself. What's one skill you learned in this program that you didn't expect to?
Okay, so one big skill I learned is like team collaboration on GitHub. Before, I just thought GitHub was just a random website where I just was supposed to download apps and steal other people's code. But during this course, I learned that GitHub and Git is just beyond that. It's like a really important tool for team collaboration and keeping our code up to date, and of course like version control, so that we can go back to our code when something messes up.
That's awesome. Second question. What was your UAV's mission and how did your design meet that challenge?
Okay, so basically, I mean, it's pretty obvious as you see this course. So our transmission was to follow this line and go through the obstacles. And to do that, our mission was divided into two parts. So one's like the front-facing cameras part, and one's the down-facing cameras part. So basically, we had to count mounts to mount the two cameras in their various angles. And then, so we split tasks. So like down camera was basically running linear regression, so it could follow the line properly. And while the front camera was just like detecting the air attacks on the obstacles, so we could then control like the altitude the drone was to like go through the hoops and whatnot.
Awesome. Thank you so much, Jimmy, and good luck today.
Thank you.
For families and friends who are in the stands who wish to see the presentations go on live, we have a live stream online. If you check that out, you should be able to see the screen. Thank you. we have one member from the team of Lynx who's currently testing their drone. Do you want to quickly introduce yourself to everybody?
Hi, my name is Henry Jin.
Awesome. Where are you from, Henry?
Connecticut.
Awesome. So quick question about your team. How did your team divide up responsibilities for this project?
So we divided it up quite nicely. So we had so there is one main thing about each aspect where it's a limiting factor. For example, when we're working on the Raspberry Pi, only one person can type on the keyboard. So it would be inefficient for all 5 people or all members of the group just to be staring at that one person who's typing typing on the keyboard. So how we divided it was basically 3 people were working on the drone and specifically the line following and testing with that. And then another 2 people were working on specifically the AR tags and how to avoid the obstacles. And after we finished the line following and it worked really well, we went on to integrate the 2 other people into the code, to the code that we were using for the line following, and then test with everything. And we're still currently testing.
Awesome, right on. Second question, what part of the UAV course pushed you out of your comfort zone?
I would largely say learning about ROS because or robot operating system because it's right now it's version 2 and version 1 was released 2010-ish. And so how basically it works is you have different nodes where you subscribe or publish to the information that's given. Like for example, a camera would be publishing to another node and it would publish the images constantly and you have to call on that node to give you the correct information. That's basically how it works, but learning about how that works and the intricacies of that, and especially like after it started not working for us, we just kind of switched over to Mavlink, which is similar to ROS in the sense that you're still calling for information, but now it's on different Python files.
Awesome. All right, thank you so much, Henry, and best of luck today.
Thank you.
Another fun UAV fact for you all. The first UAVs were actually pigeons, used in World War I with small cameras strapped to them to take aerial photos. No joke, spy pigeons were a real thing. For this attempt, they will be removing all obstacles from the path. It will only be a line-following mission.
A reminder for everyone, with the obstacle removed, we will take the best time, but any course completed with obstacles will rank higher in our final evaluation.
And links us off. Slightly unsteady at the start, but it is wavering through. The oscillations have reduced entirely. They're back. And Lynx has gone autonomous. Coming up on this first slight curve, it has done it perfectly. Coming up on its first bigger curve, follows the line seamlessly. Perfect rotation. Proceeds on to the next curve. Slight waver, but it is steady still. Lynx has stagnated slightly, but it's still on track, on path. They have decided to land Lynx, and they would like to restart this attempt. Up until the third curve, the first attempt did go very great. Quick turnaround for Lynx, they are up and at it again. And Lynx is autonomous. Much more steady flight this time around. Perfect line following path. Slower, but more accurate. Perfect turn here, coming up on where they called it quits last time, and slowed down, but still very accurate coming up. Wavering way off track, right back, a little too far. They will be landing. And that's attempt 2. Three minutes. And they are up and at it again for attempt number 3. Slightly unsteady. Steady now. And Lynx is autonomous. Following the path faster this time. Very little oscillations. And coming up on their hardest obstacle so far. And once again, unfortunately, they wavered slightly off track. And they have landed. Farthest distance for Team Lynx so far. They will be changing a battery. Final run for Team Lynx. Lynx is in the sky, high for their final attempt. Back to normal heights. Steadying down to go autonomous. And Lynx is now autonomous. Coming up on their final attempt, they're slow, paced, steady, and accurate. Smooth rotation on the second curve. Very steady flight, very little oscillations. They're coming up on the part of the track where they have had the most trouble so far. And they have seemed to be beating it seamlessly. Moving on to the rest of the course. Slightly off track, but they are following the curve. New territory for Team Lynx. They have made it very far in this attempt. Slight turbulation. It appears to be stagnant in the middle of the course. They have decided to land. Give it up for Team Lynx, everybody.
Great job, Team Lynx. Team Lynx now has a quick presentation to show all of you about the skills they learned these past 4 weeks. Take it off, guys.
All right, so we are Team Lynx. My name is Jacoby Adwin.
My name is Anthony.
I'm Henry.
I'm Keyshawn.
I'm Prem.
So our drone, in terms of hardware, is a modified Holybro X500 V2, which is a long name. It's a development kit intended for helping developers get access to the PX4 architecture. It is an X4 drone configuration, very standard, with a Pixhawk 6C Mini, which allows us to control the drone's autopilot. And we use a Pi 5 to send data to that Pixhawk and directly talk to the motors. We also have custom 3D printed mounting on the drone using the BeaverWorks ABS printer, which was graciously given to us for access. So we mount the Pi 5 and the cameras to that. For cameras, we run 2 ArduCam Module 3s. In terms of power, we use a 14.8 volt lithium polymer battery.
In terms of software, we use the PX4 Autopilot, which is the firmware on the Pixhawk, and that's what we use to control our drone. It reads sensor data that's on our drone and executes commands that we give it. We also use Mavlink as our communication protocol, which is specifically designed for drones. We transitioned from ROS to Mavlink, and we'll explain why in a later slide. And basically what Mavlink does is it transmits all the control data from the Pi 5 to the Pixhawk. We also use Q Ground Control, which is an application that runs on our laptop, and it's able to communicate with the Pixhawk via a telemetry radio, and it provides a GUI for monitoring, arming, and configuring the drone. We also use OpenCV. This is for the line detection, for the AR tag detection, for feature extraction, and much more.
All right, so one of our capabilities is the actual line following, and the main way that we did it, as everyone else, was with a linear regression. So we basically filter the video feed that we get from our bottom camera, and then we have a threshold so that we only take an account for pixels on the actual image that are above a certain brightness. So then that will be the white LED. And then after we get those contours, we apply a linear regression that gives us the actual line that we want to follow, and then we can get Vx and Vy from that line. And that's basically how we tell the drone to what direction to go. And then for the actual curves, you can get your yaw error by using, you can still use a linear regression, and you can just find the arctan, which it gives you basically it fits the line. It's not going to be a perfect, you're not going to properly follow the line, but it's the best possible turn that your drone can do. And another thing about line following is we also tried different ways. One of the methods we tried was drawing a spline, because that would better, that would make our curve following much better, but we thought it was inconsistent, and we decided to just go with a linear regression.
Another one we use is the OpenCV vision pipelines. So OpenCV is a library for image processing, image filtering, and other stuff, as said previously. We use it to detect and follow the LED lines, which the OpenCV, we use it to filter out all the noise and get the LED line through a mask. And then we can calculate the regression line and then the velocity vector to be passed to a drone to tell it to where to go. And another thing we use is the AR tags or our RUCO tags, and it calculates the relative position of the drone relatively to the AR tags through camera transformation matrix, and that will let the drone know its relative position to the AR tag and go based off that to the position of the AR tag.
So we had a few major failures, especially with ROS. The robot operating system, like I've discussed before, was something that just did not work. It acts like a middleware between all our functions, and then it communicates with ROS, and then ROS communicates with Mavlink, which is the standard communication service on all flight controllers. So using ROS, the benefit of ROS is that you're able to slot in, instead of an actual drone, we can slot in like a simulation, which is really beneficial for testing software and stuff. But when we slotted in our drone instead of the simulation, we ran into a few major errors, especially with something called micro XRCE. It's a wrapper for ROS basically, and how it works is that it has a very specific amount of memory that's allowed for communications, and we kept going over the memory whenever we communicate, so it just did not work, and that's why we switched to Mavlink.
Cool, great job, guys. Give it up for Lynx.
Wait, questions. Just don't disconnect it.
Got you. You guys are all set. We already asked questions. Now giving up for the third team of the day, Rect. So today is a UAV racing course, but Rect made a cool design of transforming their UAV into a race car also. So they'll be demonstrating that today after their run.
Starting their first attempt, Rect is up in the sky. They're steadying in for a perfect height. And Rect has gone autonomous. Battling through the first curve and coming up on the second. They are slow, accurate, slight turbulation, but for the most part, steady. Raising in height drastically now. Perfectly for the first obstacle. Rect is making great time. Through the first obstacle. Past this curve, coming up on the second obstacle. Perfect. Stellar performance from Rect so far, coming up on their final obstacle. This may be the best performance we see all day. Stagnant in this part of the course. Coming up on this last curve. Stream and steady pace. Coming up perfectly for the final challenge. Wow. Perfect height adjustment for Rect. And through the final obstacle. This is the best performance we have seen all day.
What a performance for Rect, and only being their first attempt of the day.
Give it up for Rect, everybody. With a time of 1 minute and 49 seconds, Rect is our first team under 2 minutes. With plenty of time on the clock and a stellar performance on their first attempt, Rect is going to try again to do even better. Unlike any other team so far, Rect will now be trying an autonomous takeoff. Every race you have seen so far, the teams fly the drone manually to a height, but this will be an autonomous flight entirely. Flying autonomously for the first time today of any team, Rect is in the sky. Oh. Unfortunate first attempt. We are moving the poles due to they may be the problem here. another autonomous start for Rect. They've decided to start a new position. Despite these setbacks, I would like to remind everybody that Rect has had the best performance we've had so far today. And this part of their attempt is not required by our standards. They are going fully autonomous. And they're up again. Perfect autonomous start. And now they're on to the rest of the course. Battling through the first curve steadily as they did in their original attempt. Much higher, perfect AR tag recognition. This attempt seems to be even faster than the original one. And it has gone through the first obstacle. Coming up on the second obstacle. You can see the drastic difference in how well their PID controlling goes. You can see the drone fly upon those AR tags. Cutting it close, but they did it perfectly. Coming up on the final big curve. Steady, accurate, streamlined. Halfway through. And perfectly through their last curve of this challenge. Now they're on the last obstacle. And again, perfect AR tag recognition. And that is a win for Rect. Now, can they land safely? Slight turbulation, but they are beginning their descent. Slight turbulation. And now, give it up for Rect, everybody. That was a fully autonomous flight. Time. A stellar time of 1:51 and 30 seconds will be deducted. Rect has led all teams so far. Official time is 1:21 for Team Rect, surpassing by far any other teams today.
The minus 30 seconds on the initial time of 1 minute and 51 seconds was provided as a reward for being able to take off autonomously. I was told before this race that absolutely no one could do it so I should just remove it because no team would be able to do it, but Rect has proved everyone wrong and claimed a 30-second bonus on their time.
Give it up for Rect, everybody. Attempt number 3. Once again, fully autonomous, going for an even faster time. Following the path seamlessly, as they have done so far. Perfect rotation on the first curve. AR tag recognized from afar. And the height is level. It is going very fast compared to their recent trials. Past the first obstacle. Past this curve, AR tag 2 has been recognized. Same height, they cut it close every single time. This time, oh. Unfortunate stop to attempt number 4. But that was their fastest moving drone flight. They've chosen to restart. Their battery will also be swapped. Team member Riker has come in to swap the battery. Team Rex starting autonomously for attempt number 5. Path corrected to the line immediately. Very steady flight, as shown before, and very fast compared to their recent trials. Perfect rotation, AR tag recognized from afar. Slightly stagnant in this part of the course. Moving now. Gone through the first obstacle course. Moving on to the second set of AR tags, which have been recognized much better than their last attempt. Also, much better height than their last couple attempts. They're coming up on their last big curve of this course, and their time is flying fast.
If Team Rex is able to complete this course fast enough, they might be able to hit a sub 1 minute time with that minus 30-second reduction for being fully autonomous.
They will become the first team to not only break 2 minutes, but 1 minute also. Perfect elevation. Fast flight, and now they're landing. Stellar landing coming in, and that was a perfect run.
Great job, Team Rex. Awaiting officials for final time. Results are in. It is in. This race lasted a minute 22, minus 30 for fully autonomous, leading to 52 seconds.
They have broken 1 minute, everybody.
As I mentioned before, now Team Rect will be demonstrating their race car in a UAV course. Quite the Acceler demonstration. This car design was fully made by a 3D printer using all their own tools and gadgets. This was not part of the course. This was their own personal project that they took the time out to create. We will soon have one of the members to come demonstrate their project and talk a bit about it a little bit further.
The team is writing their code for their race car as we speak. They are changing the code as we speak. Coming up on the race car, Jerry. They will be placing the car in the middle of the course, with the drone on top of it.
They are going to fly it. Yeah, yeah. No, no. It's really. I'll just.
It's gonna fly immediately?
No,
to take it out. It has landed. Tactical difficulties. Technical. Team Rex has decided they will be showing this later on. Here's their presentation.
She says we have 5 minutes. 5 minutes we each need to keep your presentation for 5 minutes. So we'll have to. Cool, great job, Team Wrecked. They will be demonstrating the car towards the end and some technical difficulties, but for now they have a quick presentation to show you guys, so feel free to do your thing.
Hello everyone, we are Team Rex. My name is Mahi, this is Jerry, Riker, Catherine, and Zoe, and we will be presenting about our experiences in this program.
All right, so to start off with the main hardware, we've got the X500 drone body from Holybro, which is just main chassis. It holds everything together. And we've got the optical flow sensor, which tracks velocity by reading the ground, how fast it moves. And the cameras are for object detection, for the AR tags, and also the line following. And the telemetry radios are to receive and send data like controller inputs and what we should do with the line following software. Yeah, and then Pi 5 is for computing all the high level computations like OpenCV, which is line following, and the flight controllers for low level computations such as just vectoring and all that. And we used ROS2 architecture at first, which send packets in nodes and allows communication between the drone and the flight controller. And CV2 is the computer vision, which processes all the images and basically takes a picture of the line and creates a computer line that shows where the drone should go. We've got Mavlink, which is the same as ROS2 architecture, but we decided to switch midway through to Mavlink because it was better. Python is the coding language we're using, and the Linux OS is a lightweight OS that we were able to run in the Pi.
So we had a couple objectives for our project. First of all, obviously this is an autonomous drone course, so we're going to create an autonomous drone to follow the course. In addition, we came here to learn, right? So we wanted to get some classroom learning and also hands-on learning on more about control systems, embedded systems, how drones work, and also learning how to use simulation. Lastly, we also really wanted to collaborate because, teamwork makes the dream work, and we definitely improved in various skills. Now, we also learned technical skills, such as how to work with the Linux OS, and also a lot of knowledge about, how to make the Raspberry Pi go with Python, and some of the physics and math behind all the stuff that's going on behind the hood in the controllers.
So despite our amazing performance, we actually did face challenges along the way. For starters, this is a very rigorous program, so it was a huge learning curve, learning how to do everything. I came here not knowing anything about hardware, and here I am. Another issue that we really had was the communication between the Pi and the Pixhawk. We went through a lot of stages, and we ended up with this one, which is Mavlink, that works pretty well. And also, we learned a lot of problem-solving skills that we didn't have before, which, especially for the line-following algorithm, which is very good, and that's exactly what I hope to gain from this program.
So some key takeaways for us. One, know your tools and how to use them. So of course, a lot of people default to ChatGPT for things these days, but also reading through the documentation and actually knowing what's going on under your system is really important. Also, question almost everything. So ask clarifying questions so you know exactly what's going on, like I said before. But one thing that definitely shouldn't be compromised on is safety. Number 3, collaboration is awesome. That's what basically got us through this program, building on each other's strengths. And finally, like I said before, documentation is key. We actually started a debugging document so that we could keep track of all the problems and solutions, and that ended up helping us a lot in the course.
So developing our drone's autonomous capability was a great experience, but we wanted to learn some more and see if we could challenge ourselves even more. So we decided to build a car that can latch onto our drone or detach, and this was actually suggested by our instructor, Shashwat. And so it's made out of mostly 3D printed parts. So I'm very grateful to Jacoby, one of our classmates, and Chris right here for helping us print all of that, and all the instructors and TAs for their support. And the idea with the car is that the drone can land on it, and the car can latch onto it. So the drone can take off with the car and take it places, or the car can drive the drone around to save energy because it's more efficient. And so we used a lot of CAD to model all of this, and there's a bunch of other things such as April tags, and yeah. Thank you.
Thank you, guys. Just some quick questions. Some good questions for the group. How did this course change the way you think about engineering or coding?
I guess personally, I come from a more software background, and this was the first time I've actually had tangible experience with hardware. So it exposed me to the world outside of software engineering, and I found it really interesting how the hardware components interact. So hopefully, I will take that back with me and dive deeper into hardware in addition to software.
Awesome. One more question. What obstacle gave your team the most trouble, and how did you solve it?
So the biggest challenge that we had was definitely the communication between the Pi and the Pixhawk. We originally were using micro-DDS, which later we found out was we faced a lot of issues, and it was about a 3-day fix, and we decided in the end to switch to Mavlink. So we kind of had to set up a whole new system in 2 days, which was very challenging.
Awesome. Thank you, guys. Round of applause for Rect.
Thank you, guys. Great job, guys. This is Ranch House? This is, I want to confirm, Ranch House. Is this an attempt 1?
Is this attempt 1? Ranch House will be starting their testing now.
This is Team Ranch House. They're going through some technical difficulties, but we'll be starting shortly.
I know Jerry's car faster than yours, but he's so for real. Team Ranch House is ready to go.
Thank you. Yep.
Okay, with me here is one member from Ranch House. I'll be asking quick questions before they start flying their drone. Do you want to quickly introduce yourself and where are you from?
Yeah, hi everyone. My name is Sai Sanjana Misala. I'm from Lenox, Massachusetts. It's in Western Mass.
Awesome. So, quick question. If you had more time to work on your drone, what's one feature or improvement you'll add?
Okay, so I would say we would add April tags. We spent a lot of time working on the code, and we ran into this one problem. We were running the Linux OS on the Raspberry Pi, but in order for the Pi cams to run, we're supposed to run it on the Raspberry Pi OS. So I would say, like, if we had more time, we would run the Raspberry Pi with the Raspberry Pi OS and enable those two Pi cams.
Awesome. Second question. How did you support your teammates when someone was stuck or frustrated?
I would say in that situation, usually our group would just like hang out outside of the course, just like get our nerves down and relax.
Yeah, awesome. Final question. Would you recommend this course to another student? Why or why not?
For sure. I think this is like a great way to get exposure into the technology that we use in robotics. And through this program, I was able to learn ROS and Linux commands, like a lot of technology that I wasn't really exposed to before. So yeah, I would 100% recommend.
Awesome. And any final thoughts to those out there? Any waves to hi to family and friends?
I would just say thank you so much to all the instructors who put in all this effort and the TAs, and also my parents who drove me back and forth from home, and yeah.
Awesome. Thank you so much and good luck today.
Thank you.
Now starting their first test flight, Ranch House. Slow start for Ranch House. Please note there will be no obstacles during this run.
Hey, oh This testing round is going wonderfully for Ranch House. Very fast, very smooth, and perfect line following. Coming up at around halfway through the course, slightly off track, but close to the path regardless, and has wandered right back on track. Coming up on the last big curve, this testing attempt is going wonderfully for Team Ranch House. Slight turbulation.
Drifting off course here a little bit. Seems to be returning back to the start point. And coming to a final stop.
Y'all are running attempts now for reals?
Ranch House is going to start their actual run with no obstacles. Best of luck to the team.
Starting off with our first timed race.
Hi everyone, I am one of the another TAs for this course. My name is Sakina Saili, and we have our student here. She's also gonna help me with the comments and everything. We'll fill you in. Thank you. Do you wanna introduce yourself?
Yeah, I'm good.
So they still have 5 minutes left for the flight, and this will be their challenge. For now, they've just been trying to test their flights, and we're waiting for them. We have an interviewee in the meantime. We're going to interview her.
Hello, Lily.
Hi, Catherine.
Hi. So, do you want to tell me something about your team that you think everyone should know?
Something about our team that everyone should know is that coming into this, we didn't all know each other, of course. No one really knew each other, but as a team, we've grown together like in our work patterns, so we know what each other's strengths and weaknesses are, and we're able to collaborate and help each other fix them and grow as engineers. And we've also become friends outside of the program. We, even a few times like a week, we'll go hang out. I gotta go help them fly.
Woo! Thank you, Lily. So they're taking off, and it's manually. As soon as the drone takes off, they're trying to have it at a perfect height so that the drone can see the line and follow the line autonomously. They're still trying to find out the perfect height for their camera of the drone. And they land.
Running into some technical difficulties. One of their cameras that was taped on late last night has become slightly tilted, making sure that following the line is much more difficult. They appear to have straightened it out now.
In the meantime, I want to introduce Reja. This is my second year working here as a TA, and Reja was one of the best students we had last year. And this year, he is a TA just like me. So this is a great opportunity for students to take the class for the first time and apply to become a TA, a teacher assistant for the next year, just like Reja. And I want to ask Reja about what he thinks of this program and the classes and everything.
I really enjoyed this program when I was a student, and so when last year's instructor invited me back to be a TA, I was super happy. I thought of all the different things that I might want to change, and I've tried to be a positive force for the students because I have a good idea of what kinds of things they're going through because I went through it just last year, so I've tried to help them out as much as possible and just make sure that the course keeps improving year upon year. Last year we barely even got a single drone off the ground, and this year we're following lines like it's no problem and even avoiding obstacles, which is very impressive.
Exactly, thank you. And also, I wanted to ask, what are you looking forward for next year? Will you be here in this program? What are you thinking, and what are your plans?
Well, we'll see if I'll be here next year. I don't know. Depends on if they want me back and what my other options are. But I've definitely really enjoyed my time here, planning out the course and doing my best to make sure everything works. I really do enjoy this kind of engineering. and teaching. So this is just such a great intersection of both of those that I can spend my time on.
Thank you so much, Rachel.
All of them?
Unfortunately, there were some issues with the batteries, so this will be their last flight. Some parts of it is autonomous, and when there are curves and stuff, it's a bit harder for the drone to adapt to the changes, so they're controlling it manually. That went off track a bit.
They're course correcting back on. Oh.
And the drone is
All
down.
right. Great job, guys.
Give a round of applause for our ranch house team. While we have the last team prepare for their flight and challenge, I will have the ranch house do their presentation. Okay, so now I have the team Ranch House introduce themselves first and go through their presentation and talk all about this program and their experiences. Please give it up for Ranch House.
Hi, my name is Prisha Kunsel. My name is Saimi Sala.
My name is Safina.
My name is Lily Kohler. My name is Haley.
My name is David Tian.
So our drone consists of lots of different types of hardware, including a Logitech camera, an optical phone sensor, a Raspberry Pi 5, telemetry radios, a Pixhawk, and the PX4 autopilot drone. All right. So our goal for this program was to assemble a drone that could fly autonomously through a series of challenges, including line following, April tag detection, and identification and obstacle avoidance.
So we started the first week with a partially assembled drone, and then within the first week we continued to assemble it and began coding with Ross. We did some labs and stuff, and then we calibrated it and flew for the first time.
Our second week, we began to develop the camera sensors. We originally were using the Raspberry Pi camera module 3s, but then in week 4, we switched to the Logitech camera. We also worked on the power distribution for our drone, so getting pieces like a BEC attached to our drone to power through the Pixhawk and the Raspberry Pi. We also created CAD models to protect fragile equipment, such as the Raspberry Pi, cameras, optical flow sensors, and any other pieces that we might have wanted to protect.
Okay, so the third week, we spent most of it just working on code and software. So we began working Gazebo to simulate our flight path, and we gained exposure to the process of debugging.
All right, in the fourth week, we started our challenge week. We were working on the final touches of our drone. We assembled the final parts of our drone, and we started writing the final software for the line tracker. Halfway through the week, we figured out that it was not a good idea to use ROS, so we started using MavLink and Mav SDK to get our drone to fly.
Okay, so for the fourth week, like David was saying, we had to switch up our entire communication system from ROS2 to MavLink. So, yeah. And anyone else want to questions? We're ready for
Thank
questions.
you so much, Team Ranch House. Reja has a question for you guys.
Yeah, people have been talking about Mavlink and Mavros and DDS for the past 2.5 hours. Could you explain what all those do and what the difference is for our folks at home?
Okay, so MavLink is basically the communication system for PX4. PX4 is our flight board. It's like it's what runs the brain of the flight board, basically. And MavLink is what the drone understands. It's like how it communicates. And in order for us to send in code, we have to translate it to MavLink so that the drone can perform the commands. And initially, we did that using ROS2, which is basically the middleware. So we can write code in Python, and ROS2 would do the conversion behind the scenes. But we realized that ROS2 wasn't very effective for our objective. So we eventually ended up switching to MavLink. So we started doing Python threading, which is basically running multiple Python files using threading is just a topic in Python where you have to where you can run multiple files at the same time. So we did that, and we directly wrote our code using Mav SDK, software development kit, so that we can get the drone to understand MavLink commands directly.
Thank you so much. So I have 2 more questions for you guys. And for our guest here watching us, this is a very intense class because the time is too short and there's too much things that we have to cover. And most of the times, instructors and TAs like me, we also figure out things walking ahead with the students. So I just want you to know that how incredible our students are right here. And my question is, since the time was very scarce, what would you guys do differently if you had a little bit more time?
If we did have a little bit more time, I think that we were discussing that we'd also add in an upward-facing camera, because we developed code for to detect the tags on the obstacles, but we didn't have time to actually put in the upward camera. So if we did have more time, then we would.
Okay, thank you. And the last question for your team. Looking back through the last month, what was your favorite part and what was the most challenging part?
So I think for our team, it was a lot of the splitting up the tasks and kind of balancing all the work. As you mentioned, it's a short time crunch and there's a lot of things to get done. So a lot of the work was dependent on each other, and I think that was definitely the hardest part. The easiest part was definitely our communication, our strengths all worked really well together. So I really was interested in hardware, and some of them were interested in software, and so it really balanced out pretty well.
Thank you guys so much. Give it up for the Team Ranch House.
Coming up next, we have Team Bell Boeing. They are actively working on code, so they're going to do some manual tests first and later incorporate autonomous flying to try to follow the line.
This is our final team, so be a little bit more patient with us, and yeah. The drone has take off autonomously at this point.
Get in. Any team. Hello, hello. Can you introduce yourself to the audience?
Hi, I'm Prisha Kunsel, and I was part of Team Ranch House.
Wonderful. So we talked a bit about your journey on the team after your presentation, but I want to dig a little bit deeper into exactly what you liked working on most in the drone. What was kind of your thing? Did you really like doing the line following, the AR tags, the math behind it? What's your passion?
I think I really liked the actual coding of the drone. I really enjoyed figuring out the logic on how to make the drone actually work. For example, when we were figuring out the Aruco markers, which we didn't actually get to implement because, as Haley said, we weren't able to get the upward-facing camera in time. I really enjoyed figuring out how to figure out, using the relative position, how we could figure out where to tell the drone to move.
Awesome. What about your least favorite part? What did you always give to another teammate that liked it more?
Honestly, if I'm being completely honest, it was the errors that were my least favorite part. I'm sure many.
Mine too.
I'm sure many people in this course and the entire program could relate. But we did our best to work through those errors, and we got here today. So.
Yeah, I want to dig a little bit more into that because I think a lot of the folks at home, they only see the final project. They don't see this random syntax error that takes you like 3 days to debug and having to read like 100 pages of documentation. So how do you stay motivated and keep working even through those very rough and confusing problems that come with developing an autonomous drone?
So the one thing that kept me going forward personally was the prospect of actually getting to see the drone fly, because it's not every day that you can make an autonomous drone. Yeah, I was just really hoping that by the end of this program we would be able to see, by working through the errors, and our flying drone.
Yeah, looking back on this program, what do you think you would change? What was kind of your favorite part? And would you say, overall, you enjoyed it and would want to do it again?
I think I would want to do it again because I love engineering, and as I said, I love the actual coding of the drone. Yeah, looking back, that was, yeah.
Awesome. All right, thank you so much. All right, and from Team Bell Boeing, we have
Andrew Wang.
Andrew Wang. Where are you from?
I'm from Texas.
All right, we got anyone from Texas here? All right, I hear some applause. All right, so tell me, Andrew, what are we working on right now in this drone at the very, very, very last minute?
So we ended up going with Mav Ross, which had a ton of bugs, but we're currently working through it. We're implementing the I and D in PID, and that's what we're currently working on.
What are the I and D in PID, and also what's the P?
The P stands for proportion, the I is integral, and the D is derivative.
All right. So I heard that late last night, your drone got into an almost fatal crash, and you had to work through that. Can you tell me exactly what happened and how you're working through that?
Yeah, so we were hovering over the line, and then we started our program, and unfortunately, I think the optical flow wasn't calibrated correctly, and it launched into the ceiling net. And yeah, a lot of our 3D prints broke, but we ended up fixing them today with hot glue.
So you hot glued the remaining pieces together, and that's staying mostly stable?
Yeah, it's mostly stable. Of course, it's not as stable as it used to be, but it's good enough to get the job done.
All right. Well, I'm glad to hear that we have it somewhat working, especially in a long program. It can be a little disappointing if things start to crash at the last second. But looking back on the program, what would you say was your favorite thing that you got to work on?
I think a lot of the math was pretty cool, like learning about the linear algebra and translating the positions, all that. That was pretty cool and new to me.
All right. I'm glad to hear it.
Thank you.
What about your least favorite part?
Yeah, working with like Ross and Mav Ross, that it had a lot of errors. That was pretty bad. I'd say that's my least favorite part.
Yeah, I think that's been a trend so far today.
Yeah.
Anything else you'd like to add?
I learned a lot. I think failure is a part of learning, and yeah, I really love this program.
All right, thank you so much. Joel, you want to get interviewed? All right, they are trying fully autonomous flight now, having finished their manual testing. All right, welcome back, Anubar. How was lunch?
It was wonderful.
All right, we're about to start fully autonomous testing for the NASA team. NASA. NASA. Oh no, Bell Boeing, sorry. Bell Boeing, apologies. Okay, what is your team name?
Our team name is DDS Bell Boeing.
Okay, there you have it. Fully autonomous flight for their last attempt. And here we go.
DDS Bell Boeing has taken off for their fully autonomous flight test. Some slight turbulation on the front end. Slightly off track, but back on track with this path. 30 seconds left on the clock. Slightly stagnant flight behavior.
Perhaps some slight manual correction.
They have skipped part of the course.
It is off the far corner, trying to relocate. Back on track.
Coming up through their last curve of the event. A very speedy finish.
A very speedy finish. All right, congratulations, DDS Bell Boeing.
Give it up for DDS Bell Boeing, everybody.
Hello, we're Team Bell Boeing, and we're in the Unmanned Aerial Vehicles course. My name is Andrew Wei.
Hey guys, my name is Abi.
Hello, my name is Abhay.
I'm Stephanie. I'm Azalea Tang.
So our mission was to build an autonomous drone that could follow a line through obstacles. And we learned a lot of lessons through this, such as robotics, physics, linear algebra. And collaborating with a team was very valuable, and learning to build team dynamics and work effectively together was also very important.
So we work on line detection, tracking algorithms, calibration using camera sensors, a lot of OpenCV, and of course testing and testing and testing again, and just debugging the code, finding errors, edge cases.
We also worked on real-time obstacle avoidance. To push our boundaries and inject some extra excitement into our work, we engineered a dynamic obstacle dodging system, or dodging tennis balls. And unfortunately, we didn't have the opportunity to test it outside the simulator.
So we ran into a few struggles throughout our journey in the course. So first was fine-tuning the line following for accuracy. This was probably the thing we struggled with the most because we were working on it until the very end. And a lot of it had to do with the Mavros and the DDS, which a lot of other people already talked about and we can go into later. But there are also a few other things like calibrating the optical flow sensor, losing detection while flying due to real-world constants, and losing telemetry radio connection, which would disrupt our tests.
So a few more struggles that we went through was using the micro agent versus MavLink. We ended up deciding not to convert and converted to MavROS instead, which still posed a lot of problems because we still had to convert to the world frame, and it was just all really difficult. We also had a lot of error in our line falling detection, having to do with the yaw, because at first we couldn't get our global yaw position, and then we also crashed a lot of times, which threw off our calibration, especially with our optical flow sensor.
Yeah, so some of our breakthrough moments, we were the first to fly and first to break a propeller. We had line detection working in real time, and also we implemented a dynamic obstacle avoidance for tennis balls.
So we learned a lot of technical skills, importance of finding solutions in collaborative environment, testing, collection, data collection, fix, and repeat.
We'll go back. And also, in this picture, you can see we also developed like a polynomial regression algorithm, but which we didn't end up using. Yeah. Thank you.
All right, great job, guys. And in our last couple minutes, we have the drone attached to a car that is going to try to work this time. But congratulations, DDS Bell Boeing. You did a great job.
Thank you. Thank you.
You want to commentate? Loki forgot about it. Well, I asked Andrew questions before.
Oh,
do you want some Andrew questions? Do you want them?
OMG. Oh, wait, okay, that's a lot of pressure. Wait, what is this supposed to do?
It's a UGV attached to a, I mean a UAV.
I know. What is this supposed to do?
It's just supposed to detach.
Is it gonna fly?
All right. They are taking off, flying manually with a heavy car attached to it, which is why you can hear the propellers are much louder. Oh, a premature takeoff. You can see the clasps appear to have opened one after another, or just disconnected entirely. That may be all we have time for, but it has worked successfully before, and soon I believe we will see the car roving around on its own. there we go. Our two vehicles flying in sync, drone controlled manually. The car set on a default program to drive in a square, but it is nonetheless very impressive that in addition to having the fastest time in the entire course, they had their own personal project that yielded such great success.
We will have to ask everyone to go back down the stairs for the final wrapping up of the event.